In this section, we will see an introduction to the idea of parametric equations. So we want to understand how parametric equations work and how to use them. So think back to when you first learned how to plot curves. Maybe this was in high school, some algebra class, and think about plotting the curve y equals x squared. Probably the way that you started was to make an xy table. And we thought of x as the independent variable, and y was the dependent variable. Y depends on x. So x is considered the independent variable. Y is the dependent variable. That just means that y is a function of x, or y depends on x. And if we thought about plotting one of these curves, we would generally create some points. So we'd put in some different x values, maybe -2, -1, 0, 1, 2, and then we'd write the resulting y values. So we'd square -2 to get 4, square -1 to get 1, 0 squared 0, 1 squared 1, 2 squared 4. And then we'd plot the points in the xy plane. So we have the x-axis, y-axis, and 0, 1, 2, 3, 4, -1, -2, +1, +2. So we have -2, +4, that's one of the points. -1, 1, there's another point. 0, 0, 1, 1, 2, 4. And we know from experience that this graph is the parabola. So it looks something like this. And we would connect these points with a smooth curve and get a rough picture of what the graph looks like. That's something that we've seen previously. Now, in this section, we are going to study curves where x and y are independent of each other. But x and y are each functions of a third variable. This variable is called the parameter. And we'll often use the variable name t to denote the parameter. Sometimes we'll use a theta or something else, but generally we use t to denote the parameter variable. So we don't have a function relating x and y. Rather, we have two functions, two different equations, an equation for x and an equation for y. And before we go any further, let's look at an example of this. So in example 1, we want to sketch the curve defined by the following parametric equations. Here we have two equations, two functions. X is a function of t, and y is a function of t. X and y are independent of each other, but each of them depends on the variable t. So we want to sketch the curve described by these equations. We could even write here, and sometimes this is useful, we could write x of t, just to emphasize the fact that x is a function of t. We could write the second equation as y of t. So we want to sketch the curve described by these, and we'll do this using a similar concept to sketching curves using just x and y. We will make a table, t, x, y. T here is the independent variable, and x and y both depend on t. So let's just use a couple values here for t, -2, -1, 0, 1, 2. We could use any representative values that we want, but this is a good start. So now we take these values for t and we plug them into the x and y functions. We'll get x and y values. These will give us points on the curve. So first of all, let's plug in the x values, or the t values, into the x function. So we first plug in -2 for t. -2 plus 1 gives us -1. That's the corresponding x value. Now we plug in -1 for t. -1 plus 1 equals 0. Once again, we're taking this equation for x and we're plugging in different values for t according to our table here. Plug in 0 for t, and x equals 1. Plug in t equals 1, x equals 2. When t is 2, x is 3. So we get these values for x, -1, 0, 1, 2, 3. Now, do the same thing for the y function. So when we plug in t equals -2, we have 3 minus 2 times -2. -2 times -2 is +4. 3 plus 4 is 7. So when t equals -2, the corresponding y value is 7. Now we plug in -1 for t. We have 3 minus 2 times -1. -2 times -1 is +2. This equals 5. Now we plug in 0 for t. So 3 minus 2 times 0, that's simply 3. Now we plug in 1 for t. 3 minus 2 times 1. 3 minus 2 is 1. Now we plug in 3 for t. And we have 3 minus, we plug in 2 for t. Plug in 2 for t. We have 3 minus 2 times 2. And we get 3 minus 4, -1. Notice here that these all have a difference of 2. 7, 5, 3, 1, -1. We're subtracting 2 each time. And if you think of the equation here, then that's really what's going on. We're subtracting 2 as we increment t. All right, what does this give us now? Well, these are points in the xy plane that are being described by these parametric equations. So let's write down what the points are. The points that we found so far are -1, 7. So that's a point on this curve, -1, 7. And then we have the point 0, 5, x equals 0, y equals 5. That's another point. So 0, 5. Now we have another point, 1, 3. And then we have 2 more points, 2, 1, and 3, -1. So we have the x values here. We have the y values. And these are the different points that are being described by these parametric equations. So let's plot these and see what we get. We'll write the xy axes here again. So here's x, here's y. And let's see, y goes all the way up to 7. So 1, 2, 3, 4, 5, 6, 7. X goes from -1 to +3, -1, +1, 2, 3. And y goes all the way down to -1. So first take the point -1, 7. X equals -1, y equals 7. There's that point. Take the point 0, 5. X equals 0, y equals 1, 2, 3, 4, 5. Take the point 1, 3. X equals 1, y equals 3. Take the point 2, 1. That's right here. And the point 3, -1 right there. Now, just like we did when we plotted just regular old xy equations, we join these points with a smooth curve, and this looks suspiciously like a line. In fact, it is a line. So, using these parametric equations, we obtain a graph of a line in the xy plane. Now that we've seen an example of what parametric equations look like when we plot them, let's talk about some more general ideas of parametric equations. So, often the parameter value t ranges between all real numbers, but sometimes we can choose to restrict t to a finite interval. This will give us just a finite portion of a curve. So in the example that we just worked through, if we had restricted the values of t to just be from -2 to +2, then we would only get a line segment. We would get this segment of the line, not an entire infinitely long line. So we could say that t just ranges from -2 to +2 rather, and that would result in just a finite line segment. So we can restrict the parameter to a finite interval and only get a finite portion of a curve. What else can we do here? Well, as t increases, more of the curve is traced out. And what this does is gives a direction to the curve. Let's look at the example that we just did. As t increased from -2 to +2, the curve was sketched out in this direction. So we could add an arrow here to describe how the curve is sketched out. The curve moves in this direction as t increases. So parametric equations have a directionality to the curves, and this is especially useful if we want to model trajectories or an object moving. We can add a direction to how the curve progresses. In some instances, we can remove or eliminate the parameter, get rid of the parameter t to obtain what's called a Cartesian equation of the curve. Cartesian equation just means an equation in terms of x and y. So we think of the normal Cartesian coordinate plane, that's just the xy axis. So a Cartesian equation is kind of the opposite of a parametric equation. We're used to working with Cartesian equations. Like x squared, y equals x squared is a Cartesian equation. So if we can get rid of the parameter t, we get a Cartesian equation. How do we do this? How do we eliminate the parameter? What does that exactly mean? Well, to eliminate the parameter, typically we'll perform 2 steps. We look at our parametric equations. So we have a parametric equation x of t, this is some function of t, and we have another parametric equation y of t. We'll take one of these equations, whichever one seems most convenient, and we'll solve one of the equations for t. Once we've done this, we substitute the expression for t into the other equation. Now, let's look at an example to see how this works. So example 2, we want to take these parametric equations, eliminate the parameter to find a Cartesian equation for the curve. So we're kind of running out of room here, but we can do the steps up here. The first step for example 2 is to solve one of these equations for t, whichever one looks easiest, whichever one we'd like. I think the first equation is probably the easiest to solve for t. So we would get t equals x minus 1. Now the second step to eliminate the parameter is to take the expression for t and substitute into the other equation. So we solve the first equation for t. Once we've got an expression for t in terms of x, we take that expression and we plug it into the second equation. So we would have y equals 3 minus 2t, and now t is x minus 1. We can simplify here. 3 minus 2x, negative 2 times negative 1 is plus 2, so we'd actually have a 5 minus 2x. So when we eliminate the parameter, we get the Cartesian equation, y equals 5 minus 2x. Let's think of this Cartesian equation compared to the graph that we just gave for the parametric equations. This is the equation of a line. Thus, the line has a y-intercept of 5 and a slope of negative 2. Check out the picture that we got. We have a y-intercept of 1, 2, 3, 4, 5, and the slope here, rise over run, is negative 2. So this makes sense. The Cartesian equation that we get describes the line that we got from the parametric equations. Now, when we have a Cartesian equation, we lose some of the information. For example, this equation is an infinitely long line. When we had parametric equations, we could restrict the parameter to only have a finite portion of a line. Also, in the Cartesian equation, we don't have a direction to the curve. It's just a line. When we have parametric equations, there is a direction involved. In this case, the direction was downwards like this. We could redefine the parametric equations to have the same looking picture with a direction going upward like that. So parametric equations give us a bit more flexibility with curves, and we'll see some more examples of that as we continue.